A really common force that we encounter in physics is the force of a spring. And the other reason that this is going to be interesting for this particular chapter or for the concept of work is that this force is an example of a force that depends on position. So when we calculate the work, we're going to be using the integral. But let's back up a minute and think about the force of a spring. So the force of a spring is kind of special, as I said. And we're actually going to run into this later on in the semester, because we're going to see that the force that a spring exerts on an object actually is a special kind of force that causes, as an outcome, simple harmonic motion. But just for today, we want to get a basic idea of the force on a spring. Now, when we talk about a spring and we designate its position, we do so in a special way. There's a position where the spring is at what we call its natural length, and that becomes our x equals 0, because we're going to measure from the end of the spring. I say it's at its natural length because at this instant in time, the spring isn't being stretched and it's not being compressed. And so the measure of stretch and compression is what we're going to be looking for when we think about this x. Now, so here in this first picture is the spring at its natural length. The position of the spring we say is 0 because, again, it's not being stretched or compressed. So looking at this expression now, this force that the spring exerts, you can see there's this negative sign right here. And so what it means is that the force is going to have the opposite sense of what x has. So when x has a positive value, the force of the spring is going to be negative, and vice versa. When the spring has a negative position, which means it's compressed, then the force of the spring is going to be in the positive direction. Now, K is called the spring constant, and it gives us a sense of how, well, the language we use is stiffness, how stiff the spring is. And what it means is how much force is needed to either stretch or compress the spring by a certain amount. K will be a value that a particular spring will have. It'll be characteristic of that spring. When K is a high value, we say that the spring is stiff, which means it's very hard to stretch or compress. And the opposite is true. If K is relatively small, it means that this is a spring that is very easy to stretch or compress. All right, so now let's take a look at the second scenario. In this case, you can see that the spring has gone past the x equals 0 location. And so now the position of the spring now has a positive value. But because the force of the spring is in the opposite direction, what that means is that in this scenario, the force of the spring would be to the left. So the idea is that something must have been stretching the spring, but the spring wants to get it back to its original x equals 0 location. So the force the spring exerts is in the opposite direction of the displacement, and it's going to be to the left. In the last picture, we see that the opposite is true. In this case, the spring is compressed. The displacement of the spring is to the left, which means the force of the spring is going to be to the right. So those are all things that we have to take into account when we're thinking about a spring. Now let's think about the work that the spring does, the work done by the spring. Well, as we already said, the force of the spring is equal to minus kx. And so when we're calculating the work, the first way that we saw work defined was simply the dot product of the force with the displacement. This isn't really going to work for us because we see that the force changes as the position changes. So we want to use this situation where we would be thinking about the calculation of the work as an integral. And so now, instead of just overall displacement, which we were calling S, we're going to look at an increment of displacement, which is ds. For our spring, this is relatively simple because the force that the spring is exerting, as we've indicated here, we've chosen to say it's in the x direction. And so we're just going to say f of x, and then the displacement that's in that direction would be dx. So going from here to here, because the force and the displacement are parallel to each other, we don't need to use the dot anymore, because in a sense we've taken the dot product and found that it's just the product of the force and the displacement because of the fact that they're parallel to each other. Now we can replace the force by minus kx times dx. And we're going to just say that we're going to go from some initial x position to some final x position. When we integrate minus kx dx, we get that it's minus 1/2 kx squared. So remember that when we integrate a polynomial, the power increases by 1 and we divide by that new power. So x went from a power of 1 here to a power of 2 here, and then we divided by 2. Of course, the negative sign came along for the ride. We can't just ignore it. Our endpoints where we're going to evaluate our integral are at x initial and x final. The negative sign makes things a little tricky as we're evaluating at the endpoints because we just have to be careful. And we notice that this ends up to be minus 1/2 kx final squared plus 1/2 kx initial squared. And so this can be the way that we calculate the work done. This is by the spring, because we have used the force that the spring is exerting. And so it's this expression, which is negative, plus this one. We could rewrite this and write it as like that if we don't like to have the negative sign first. But in any case, we will have to kind of remember that this sign of the final is negative and the sign of the initial is positive. And it's the work done by the spring as we go from some initial position to some final position. Notice that in this expression for work, it doesn't actually matter if the x is negative or positive because we're squaring it. So even if it's positive, even if it's negative, when we square it, we'll get a positive value. Now, I wanted to just bring up the idea that a lot of times we are not only really thinking about the work done by the spring, but we're actually thinking about the work done on the spring. Now, it seems like a very subtle difference in language, but it means a big difference. Okay, I'm going to say it one more time just to see if you note the difference in the language. In the previous slides, and up until now when we're talking about the spring, we were talking about the work done by the spring. But we never really talked about how did the spring stretch. It didn't happen spontaneously. there had to be an external force that caused that stretch. And so let's just think about the force that had to stretch the spring. And we're going to think about the force acting on the spring. And what you see right here in this scenario is, of course, using the top as our reference point, we can see that they're trying to show us where the unstretched, uncompressed spring is. So this is where our x equals 0. And then we see right below, clearly the spring has been stretched. Well, the force that was exerted on the spring to make it stretch, so has to be the force on the spring has to be equal and opposite the force by the spring. And so since this is minus kx, this is the force by the spring, the force on the spring is just equal and opposite, and it's just equal to kx. So sometimes we might want to think about the work that we do as we stretch or compress a spring. And in that case, we don't have the negative sign in the force. And as you can see right up here, we're just saying it's equal to kx. The reason for that is that in order to stretch it or compress it, we just have to apply a force equal and opposite to the force that the spring exerts. In that case, we could say that the work done on the spring would be equal to, and this is as we stretch it or compress it, would be equal to 1/2 kx final squared minus 1/2 kx initial squared, which you notice is equal to minus the work done by the spring, which we had found previously. Now, I acknowledge that this the first time around can seem kind of confusing, but I want you to sort of take some time and really sort of think about this and really try to reason through it. All that we're saying is that there are two ways to sort of look at this. We can look at it from the viewpoint of what the spring is doing, or we can look at it from the viewpoint of what we're doing to the spring. And those two forces have the equal magnitudes, but they're opposite in direction. And that is what ends up giving different expressions for the work by the spring compared to the work on the spring. So we're going to look at springs a lot. It's sort of a common force that we deal with. So we want to get used to them.